Good day, I'm Dr. T and welcome to my office. So today I'd like to start a new video series called Lies from the Textbook. These are things that are typically taught in lower level chemistry courses, although I'm not necessarily going to be limited to just lower level or just chemistry. And these are things that are taught in a way that either implicitly or explicitly conveys information that is not exactly true, that might be true most of the time but not all of the time, or is an oversimplification to the point of inaccuracy. And so in today's episode, I would like to talk about one of the early topics in general chemistry, and that is isotopes. So early on, probably within the first couple of months of the first semester chemistry class you take, you will learn about isotopes. Isotopes are going to be atoms. Atoms are made of protons, neutrons, and electrons, and isotopes are the same except for they have a different number of neutrons. And you'll be taught a couple of things. One, the different number of neutrons affects their mass, and this will generally lead into atomic weights, weighted averages, formula weights, and whatnot, and that's usually where we focus on when it comes to isotopes. Then it will probably be an aside that, oh, by the way, we'll come to that a little bit later when we talk about radiation. Because some isotopes, the arrangement of protons and neutrons leads the nucleus to be stable, so it just kind of sits there. Whereas in other isotopes, that's not a stable arrangement, what we call radioisotopes. And these will degrade, sending off radiation in one form or another. But it will either be implied or explicitly stated that because they are the same element, they have the same chemistry. Well, they have almost the same chemistry. And this is a little bit of a rabbit hole, which is why it's usually dodged. The electrons are going to be buzzing around the nucleus. I'll let you see other videos for why I use the very non-technical word buzzing here. But they'll be buzzing around the nucleus in basically the same way, so they're going to be doing their thing, and they're the ones that control the chemistry. So far, so good. The same chemistry, same bonds, etc. Turns out, though, the nucleus does actually affect the bonds, though, but in a really interesting way. Atoms are always vibrating. Everything is in constant motion. Every atom is always vibrating. And because of that, that vibration will stress the bonds they make. Okay, not a big deal. It's not much of a stretch. And so as they're vibrating, they're doing their thing. But here's an interesting feature of vibrations. Like at the macroscopic level of harp strings or in the atomic level of atom nucleuses, the heavier something is, the slower it vibrates. So heavier isotopes are going to have a slightly slower vibration to them. And as such, they're going to stress out the bonds slightly less. So their bonds will be a little bit more stable than their lower weight isotope cousins. Well, this affects the chemistry. In order for a chemical reaction to take place, pre-existing bonds are probably going to have to be broken, or pre-existing interactions is probably a better way to say this because it doesn't have to be a true bond. But those are going to have to be disrupted. The more stable they are, the more energy it's going to take to disrupt them. This is going to be part of what we call the activation energy. And so now, the function that's describing the activation energy, one of its parts just got a little bit bigger. So the activation energy is going to get a little bit bigger. As activation energy goes up, the rate of the reaction goes down. And therefore, heavier isotopes will react slower than lighter isotopes. Now, here's the reason that we usually don't cover this. That difference is not much. Quite often, not enough to care about or even be detectable in many reactions. So why go into it? Well, there are a couple of cases where this is particularly interesting. The first, of course, involves hydrogen. Hydrogen comes in several isotopes. The common ones would be hydrogen, deuterium, and tritium. Hydrogen's actually such a big deal that we call hydrogen 1 just hydrogen, hydrogen 2 deuterium, and hydrogen 3 tritium. Well, if you take a hydrogen 1, so hydrogen, it's just a proton. So if you take a proton and stick a neutron onto it, you've pretty close to doubled its mass. So that's actually a pretty big deal. The reaction rate difference will be somewhat noticeable when switching from hydrogen to deuterium. The other interesting source is that of carbon. Carbon comes in several isotopes, most notably carbons 12, 13, and 14. It turns out you can actually look at the ratio of carbon 12 to 13 as well as 14 in order to figure out if a certain source of carbon likely was engaged with by a plant. See, carbon dioxide can have either carbon-12, carbon-13, or carbon-14, and plants will take those up from the air and turn them into, well, plant. Well, turns out it's a little bit easier for them to take up and use carbon-12. So plant material, or thus biotic, because that's where carbon usually enters the food chain, is from the plants. That's going to be slightly enriched in carbon-12 because it's a little bit easier for the plants to consume carbon-12 than it is carbon-13 or 14. This is a small difference, but it is measurable and it is useful to figuring out if you've got some carbon, whether or not that was a dead plant or formed from inorganic means, which are significantly less sensitive to this whole isotope thing. And one last one to cover, and that is with water and oxygen-16 versus 18. Water evaporates. Now, a water molecule that has an oxygen-16 in it will evaporate, because it's a little bit lighter, a little bit easier than a water molecule with oxygen-18. So you can get clues as to how hot it was by the ratio of oxygen-16 versus 18 in precipitation. Additionally, you can get clues as to things like non-precipitation water incurring events, like storm surges, by the ratio of oxygen-16 to 18 in, say, plants that have sucked up water or whatnot. Hopefully you found this an interesting topic, and with that said, have a wonderful day.